Welcome to the seventh video in the series. The topic this time is about some applications. This video is exciting for a different reason. This time we will move away from the fundamental theories and collision physics, and we will dive into the material science and statistical physics. The reason why this video is here is because the techniques developed so far will be used for this new material. We will discuss the QFT description of superfluidity, the Bose-Einstein Condensate, and superconductors first. Then we will go through how we can calculate everyday life quantities like temperature, pressure, or entropy from these very quantum fields. Please note that this is going to mean that we have a theory which covers around 24 orders of magnitude. I believe that's very cool. So let's get started with it. First two applications that we shall discuss are superfluids and the Bose-Einstein Condensate. 7.1 is superfluids and Bose-Einstein Condensate, or short BEC, or BEC. So let's discuss superfluids first. A superfluid is a state of matter where momentum flows without dissipation. An example here that we could give is the helium-4. So when helium-4 is cooled below, its temperature is below 2.17 Kelvin, then it becomes a superfluid, and one of the experimental results of this, or experimentally checked properties of this, is that the superfluid of helium-4 could just flow through the capillaries without any resistance. And there are really cool videos about this on YouTube. I will link them here. Flow through capillaries. With no resistance. It also exhibits the so-called fountain effect, whereby a beaker of superfluid spontaneously empties itself. That's also cool video to see. Fountain effect. From the theoretical point of view, to describe this, we need to find the Hamiltonian, as we learned so far. And that Hamiltonian should describe non-relativistic bosons interacting with a momentum-independent potential. So maybe we should remind ourselves that the Hamilton operator is the same thing as the integral, the three-dimensional integral of the Hamiltonian density. So if we write the Hamilton operator, then it will have integrals. So we start with the usual 1 over 2m. Now we have this integral just because we are writing down the Hamiltonian and not the density. And then we have the nabla of our boson field pi dagger. And then we have that twice, but as the nabla of the phi. And then we have this potential, which goes with the g. And again, since this is going to be a Hamiltonian, we need to have the integrals. And actually, we will have two integrals for x and y, because we want to have this interaction between the 2 points without having any momentum dependence though. So we will have phi dagger at x point, it's 3 vector, and interacting with the phi dagger at the y 3 vector, and this is multiplied with the phi at the y point and the phi at the x point. So all of these are operators, of course, and we should have a continuity in this, which we will include by the three-dimensional Dirac delta. So we want x minus y, three vectors. In the next step, we should quantize this. So that means that we essentially put it into a box. So quantizing means that put it into a given volume. That also includes that we discussed earlier that the phi x is the same as we had the sum for the p of the AP and the exponential of minus plus I p x. These are now three vectors, and so we have some normalization factor, and if we put it into this box which has volume v, then the normalization is going to be the square root of v. So if we plug this in here, then we will have derivatives by the x essentially. So that will take a p down, and then when we do that here, that will also take a p down. So by doing this, we will get that the Hamiltonian operator is the same as the sum for the p of p squared over 2m, which is something which you should look familiar. And we have these two operators, the a dagger p and the a p operators. This is the kinetic term. And now we have the term for the potential. And so we have four operators, one p minus q momentum with a dagger, it's an operator, and we have a k plus q, and this goes with the dagger operator, and we have then a k operator with the a p operator. And so we do the sum for all of these k, p, q momentum vectors. And this looks very complicated. And it's actually very hard to solve. So this is hard to solve. And we will need to make an approximation. The approximation uses the idea from Nikolai Bogolyov. So Bogolyov. So he said that if the system has very little energy, which also means that it's very cold, if T is much less than 1, or then the number of particles, which we call n0, the number of particles n0 in the ground state, in the state p0 is going to be large. So based on this, we can replace the a where the p is 0 operator and the a dagger operator where the p is 0 with this number, or actually the square root of this number and 0. And when all of this happens, there is going to be a change in the state of matter, new state of matter, which is called the Bose-Einstein Condensate. Bose-Einstein Condensate. So there are some fun stories with this, and Bose was really the one who figured this out, and then when he tried to publish it, I don't know, then it didn't really work out. And so then he sent it to Einstein. Then together they could actually publish it. After playing a bit with the sums, like you think about all these cases, then P is 0 and K is 0, then we get from this we get A minus Q, A, Q, A0, A0, this had the dagger, so that will just lead to an N0 of A minus Q with the dagger and AQ with the dagger. And then, if you look at the next version, that the P is 0 and the K plus Q is 0, that will lead to something like A minus Q, A0, AK, A0, where this first two were daggered, and so this will lead to N0, A dagger, AK, and so on. You look at the cases, each of the cases where these things are 0. So I'm not going to write those out now, and so on. So this leads to the interacting Hamiltonian of G over 2B that was unchanged, and so the sum of this part is going to lead to n0 squared plus 4n0. We have the sum for A dagger P and A P, where P is non-zero, plus n0 times the sum, again where P is non-zero, for AP dagger A minus P dagger plus AP and A minus P. So here we see that particles are created in kind of pairs where they have momentum P and they have momentum minus P. So the consequence of that is that when you cool these things down, these states will cancel out and we will have this state, or most of the particles will be in the lowest energy state, which is the ground state. After we diagonalize the Hamiltonian so that it will have the form of H equals the sum for the P of AP, A P dagger, AP, these are of course operators. Then the energy states EP will be in the form of P squared over 2m multiplied with P squared over 2m plus 2 and G under the square root. So if we were to plot this, so I am going to plot the energy and the P itself, or the absolute value of that P, since we have squares here. Then we get something like this. And we can say that when we are at the high momentum, then this is kind of like this part is kind of like a parabola, so it's a P squared over 2m is what's important. And at this point, the linear part is important, so that is the ng over m into the square root of p is what's relevant. And so that's very similar to what we have seen for the photons. And so we know that this is going to be a boson. And actually this part of the behavior is a boson, and it's actually called the bogolon. The naming with the bosons is that you put an on to the end, and it was the Ugly of transformation. Nikolai Bogolov was who figured this out, and so that's why we call it a Bogolon. The original bosons have a number density whose behavior is wave-like, and then these waves are quantized into bogolons. And these large momentum bogolons behave like free particles with mass m. So P is high, then like free particles. So actually, we could now look at some measurements, and that's actually what I have it up here. This plot shows the velocity distribution for a gas of rubidium atoms, and this is what we actually confirm the existence of this new phase of matter called the Bose-Einstein Condensate. So we see the distribution of how fast things are moving. On the very left, you see that things are kind of moving with every kind of velocity on this in this space. So nothing special. And then as you go on, which actually means that the temperatures are lower and lower, then there seems to be that particles will move into a state where they all behave the same way and they have this low velocity things. So everybody is in around the zero velocity state, and this is actually what how they discovered the Bose-Einstein condensate. In this last sample, you see that everything is kind of around zero, except in the middle where you have a lot of events, and then they have low velocity. There is some further fun things that we could do with these Bose-Einstein condensates. So actually, first of all, I just look at this plot, which is 7.2 from my book, and that's actually coming from the 2011 Nobel Prize. They did give a Nobel Prize for Bose-Einstein condensates. And so what we see here is that when we are at high temperatures, then particles could be described as like balls that they are just hitting each other. The relevant distances are, d, and then the density is going to be 1 over d cubed, and then there is a thermal velocity v, which is like most of the velocity of the particles go, but there is a distribution of that. As you go to a lower temperatures, then we realize that these are not really particles anymore, they are not really balls anymore, but they are made of wave packets. Like this is also true for photons and so on, but it's also true for matter, and that's what de Broglie figured out, that for every matter you can figure out a wavelength, and then they will act like waves as well. And so the next step is when we reach this critical temperature for the Bose-Einstein condensation, then all these little waves are merging into one big matter wave, essentially. And as you go to t equals 0, which is of course cannot be reached, but as you approach that, then you get this pure Bose condensate where everything is at the same energy and behave the same way. This other picture which I'm showing is here to show the double slit experiment with the Bose-Einstein condensate. So they just cool down these lithium 2 diatomic molecules, and they just made the interference experiment, and we see that this is like really measurable scales, right? It's in milliseconds, so it's around 15 milliseconds, and this 550 micrometer big plate, you have the two waves coming through the slit, and then they interfere with each other, and we see a beautiful interference pattern in the end. So this is exactly the same results that we have seen in the double slit experiment, but now this is happening with matter and at millisecond level. So the discovery of the Bose-Einstein Condensate really gave us another method to check quantum mechanics and its predictions. So it's kind of cool. Let's discuss superconductors now. 7.2 is superconductors. So superconductors are very similar to superfluids, except that they are solid materials. The building blocks of a superconductor are the so-called Cooper pairs. Cooper pairs are pairs of electrons. It's two electrons with up spin plus down spin and p plus minus p momentum. We create a Cooper pair from the vacuum using this new operator, which we will call uppercase P for P, and the dagger is an operator. It is created from the C operator that creates an electron with P and up spin, and we have another C operator which creates minus P with down spin. This is a Cooper pair as we just discussed with the definition. And the theory was actually described by John Bardeen, Leon Cooper, and Robert Schrieffer. So it's actually called the BCS model. The Hamiltonian for this BCS model is just actually coming from what we just discussed. So the Hamiltonian operator is the same as the sum for the momentum P and the spin sigma. Now that's the new thing. Energy corresponding to these momentum P, and now we have the C, P sigma dagger, and the C, P sigma operators. This was the kinetic term, and we have minus G over 2V of the sum, for all kind of momenta P and K of the uppercase P and the uppercase K dagger operators, which again is going to be created these two pairs. And then now we have the interaction between these pairs here. And then there are some super fun consequences of this. Again, there are a bunch of videos online that we can check later to see how superconductors work. But the theory behind that is really just this mathematically, that we have these pairs of electrons and they lead to a completely new set of phenomena. So now that we started to discuss superfluids and superconductors, I'd like to move one step up, which is just generally comment about material science. So 7.3 is a short comment on material science. So it's a huge subject, and we could also have 6 lectures about material science. But what I'm going to just do is that I'm going to show you the bridge between what we discussed so far and what happens in material science. So we discussed these so-called quasi-particles like bogolons, and so we should actually comment on the idea of the phonon. So in an atom, the solids are in unit cells, I don't really know what should I write here. You have all these cubes and so on. You have different kind of unit cells, and the atoms are vibrating, right? So they don't move too much, but they do move a bit. And so what happens if I push one atom down? This is actually just like touching or pushing your desk. Then you already push an atom down. So this is an easy experiment. So this vibration will push this atom down, but then this atom will move up and will push this down, and then this will move up. So there is going to be an up and down movement, which will then essentially mean that there is going to be a wave created by when the atoms are moving down and moving up, they rearrange themselves to the original position. And if so, there is a wave, then those waves can be quantized, and the quantum is named somehow. It's going to be a boson, and it's actually called a phonon because of its connection to the sound. So these are sound waves in the matter, and they are quantized into phonons. So when you touch a metallic object and it creates this weird sound, then that's because you created phonons in the material, which then bend into the air and created sound. So sound is really just a fluctuation of matter. So these are bosons, and if they are bosons, they are described with the same kind of situation as you would describe a photon. And this is not so. In the Feynman diagram picture, one of this is the photon and this is the bosons. They look exactly the same. And so essentially all material science can be described with the same kind of idea that we had earlier, that you have an electron, two electrons create a phonon. So this is now a phonon, not a photon. These are electrons. And then these phonons can decay into electron hole pairs again. Or you could say that you have an electron and then you have a phonon incoming, and there is going to be an electron going forward. And so any interaction or there is two electrons incoming and they exchange a photon, and then the electrons are going through the situation. So the same kind of diagrams that we have seen with the electron-photon interaction can be now, as they are, translated into material science and calculate the same kind of amplitudes and use them to describe different materials. The last thing I'd like to discuss is statistical physics. 7.4 is statistical physics. So I hope you see that we are going from the tiny into a bigger and bigger picture. So statistical physics deals with systems where you have a lot of things around. So we have seen it earlier that the Hamiltonian acting on the end state will give us the energy of the state and the state itself back. So this was the Schrödinger equation. And this is essentially what we will use in statistical physics as well. However, in statistical physics, you can make three different kind of systems based on the interaction. So three categories. You can have isolated systems, or closed, and or open. 7.4.1 should be about the isolated system, which means that our system has no connection to the outside world. no connection to the environment. If we are interested in how many states we can have in a system, then it's best to look at the phase space of it. The phase space can be plotted as the position versus the momentum. So a plot like this, what's x and what's b, and it shows all the possible states in the system, right? So if you can draw a spot here, that's going to be a state, and then everything which is possible will be on this plot. In the quantum world, the unit is the Planck's constant. So one state will have the area of H. If we look at one state on this plot, that, with a little p and a little x will have the area of H. So these states are called microstates. Microstates denoted with omega. So the number of states will be calculated as doing an integral for this dp dx plane when you have n particles, so you put an extra n here. And what we should always look at is the situation when the Hamiltonian for this px situation is less than the energy of the system. So they are not scattering around and things like that. They have to be lower than the energy of the system. And so this is all the space. And if you're interested in the number of how many microstates there are, then we will have to divide with the unit, which was this h, and if we have n particle, that's going to be h to the power of n. We can get the same thing by approaching this from the quantum equation gives us the possible energy states as we discussed it up here. And so we are interested in the number of states until a certain level, that was the E, and we could just add those things up. So whenever the energy is whenever the energy of a given system or a given state En is less than the our energy given in the system, we should add those things up. And so this actually leads to the so-called Heaviside function. So we have a sum for the number of states, and we do the Heaviside function, which is the theta of the energy minus the energy n, the energy of the n state. Heaviside function or step function is also called a step function if the x is negative, then its value is 0, and if the x is positive, then it is 1. So that's why we have this the other way around, and we had it here, because we only add up things in which the energy is less than the energy in the whole system. So the reason why these microstates are important is because the macroscopic state of the system is characterized by the distribution of these microstates. Macroscopic state comes from the distribution of the microstates omega. The entropy of this distribution is given by the Gibbs entropy formula. So Gibbs entropy formula is denoted with S, the entropy is denoted with S, and what we do is that we need to make a unit change where we use the Boltzmann constants. Okay, we use the Boltzmann constant. And so as I just said, that really this omega, which corresponds to the given energy, right? Because it's always what's less than the energy, is what gives this. Well, then we need to do a transformation, and that transformation is going to be the logarithm. So the logarithm of the microstates is essentially the entropy. We need to include this factor kb for having the correct units. This is very nice, as from thermodynamics, we know that the differential equation of state is given by the following formula. Maybe I should say that the equation of state, dE, that's why it's called differential equation of state, is the same as temperature multiplied with the change in the entropy, ds, minus P, pressure, and the V, the volume. If you haven't heard of this, I think at Marston there is a class called physical chemistry, or there used to be. So that's something that we could learn about how we got this result. Now I'm just going to use it. So E was the energy, T was the temperature, S is the entropy, and the P was the pressure, and the V was the volume. So if we have an isolated system, then the number of particles in the system are fixed. The number of particles is fixed. We said that in an isolated system you don't interact with the environment, so you cannot lose particles. And this leads to the following. So n is fixed, the volume is not changed, so dV is 0. Then we just left with saying that dE is the same as ds. So this then leads to our very important results by rearranging that 1 over T is the same as the derivative of the entropy by the energy. And we say N and V are kept constant. This is the notion, are fixed. We could also express the situation if we say that the energy is kept constant. If dE is 0, then we are left with saying that 0 equals the same as ds minus p dv. So from that we can express the pressure is the same as the T derivative of the entropy by the volume. And what we did here is that we said that the number of particles and the energy is fixed. And all these things are actually called the microcanonical ensemble. as our next step, let's look at the closed system. 7.4.2 is the closed system. A system is closed if there is no exchange of particles, but there is an exchange of energy. N is fixed, but E is not. So in this case, the omega will be upgraded to the Z, which is called the canonical partition function. Canonical partition function. And it includes the energy effects as an exponential. So the Z will be still the same as the h to the power of n, still the same as the integral for the momentum and the position, still to the nth power. But now comes the upgrade that we say the energy effects are coming in with minus beta h, where the h is still the Hamiltonian, and the beta is the inverse of the Boltzmann constant and the temperature together. So after we reapply the Schrödinger equation, we get that the states is the sum for n of ar minus beta en, right? So the Hamiltonian will become the energy, and the relevant function here from thermodynamics is called the Helmholtz free energy. Helmholtz free energy, and it's noted with F. So the relation between F and this Z partition function is going to be similar to earlier, minus KB T, taking the logarithm of this Z. And if we take again the differential equation of state, that is the F is the same as minus S dt minus P dV. And from this we can calculate the entropy. S is the same as minus the derivative of F by the temperature when we keep the N and V constant. To get the pressure, we can go back to our previous equations and just use the entropy result already. So we can get the P by taking the minus derivative of the free energy, Helmholtz free energy, by the volume, and keep the N and the constant. Earlier we also had an expression for the energy. We can't do that because the energy is not changing. What we can do though is that we can look at the expectation value of the energy. So the expected value is calculated as the derivative of ln z by the beta, which you remember was this 1 over kbt. So now we are only left with the third version, the open system. 3.4.3 is the open system, which you could figure out is the step when we allow the number of particles to change. Earlier we let energy change, but not the, so n isn't fixed anymore, and E is still not fixed. So this essentially leads to chemistry. In chemistry, the number of particles change. And the function, we had the omega, which then became z, is now becoming the mu, where the mu is the so-called chemical potential. And so that's why I said that it essentially leads to chemistry. So then the z will be partition function, which is now actually called the ground canonical partition function. Is calculated with the same start, h to the power of n. We have the integral for dp dx to the nth number. We had the minus e beta h, and now comes the new part, which is again going to be in the exponential form of minus beta, and now we have the mu chemical potential n, and we need to make a sum for these n and the number of particles. What we followed earlier, we will do the same thing again. We will apply the Schrödinger equation. So after Schrödinger equation, this z, uppercase z, will become the sum for the n, and this for the number of states, and the sum for the uppercase n, the number of particles. And we have the exponential of minus beta en, this is unchanged, and now comes the change, which is the beta mu n part. The potential is now called the ground canonical potential. So ground canonical potential is the uppercase phi, and we get that by taking the minus kb t ln of the uppercase z, and then we do go to the differential form. The phi is the same as minus s dt minus p dv minus uppercase n d mu. And so essentially this is the point where we really have included anything that you can think about. And so we can again get the same kind of results, that we have the entropy calculated as the derivative of this phi by the temperature. When we keep mu and v constant, then we can get the pressure out of this by taking the minus derivative of the phi by the volume and keeping the mu and t constant. Then we can get the chemical potential mu by taking minus t times the derivative of the entropy by the number of particles and keeping the volume constant. Since the number of particles changes, we cannot have anything for that, but we can have an expectation value. So again, we calculate the expectation value, and it's going to be similar. That is going to be the derivative by the mu and beta together of the logarithm of the z. And with this, we reach the end of this thing. So I'd like to recap a bit that what really happened here is that we took the Hamiltonian function of a system, and from the Hamiltonian, the Hamiltonian density, we get to the Hamiltonian, from which we got to the omega, or we could get for the z for the closed system, or the uppercase z for the open system. And for each of these, we got to things like temperature, entropy, the expected energy, the expected number of particles. We also calculated chemical potentials, and so on. So, like this is actually an extremely important result that from Hamiltonian densities, which we really used in the past, which seemed very abstract, and then we calculated in the end collision results, which is still seemingly far from everyday life. We get up to something that you can measure with a thermometer in your room. So this is the power of this quantum field theory, essentially, in the end, that and also the power of physics, that we describe so many orders of magnitudes, and they are still coming from this Hamiltonian, in which we've been discussing all along in this series. I hope you enjoyed this journey from the fundamental to everyday life as much as I did. The next step in our story is going to go to the level of the whole universe. So next week we will be discussing cosmology and a bit about how cosmology is hinting us the possibility of some new physics. So see you next week.